We're now moving on to 18.4, Structure and General Properties of the Nonmetals. In this section, we're going to describe the structure and properties of nonmetals. Kind of self-explanatory. So nonmetals have a variety of chemical behaviors. Some are the most reactive elements and others are the least reactive. They can form a bunch of different ionic and covalent compounds and are very important in biological systems. We can use electronegativity trends to predict the type of bonding and the physical states of the subsequent compounds they form. Just a reminder, in electronegativity, it decreases when you go down a group and increases going from left to right on the periodic table. Nonmetals have higher electronegativities than metals and generally are going to form ionic compounds with metals. So remember, electronegativity is the want of an atom to have all those electrons and electron density around it. So nonmetals like to have electrons to fill their octets, so they like having electrons surrounding them. When you have nonmetals bonding with each other, you tend to have covalent bonding. And then interestingly enough, whenever you have a nonmetal ion, a monatomic nonmetal ion, they're always anion. So you don't have monatomic cations of nonmetals. But they can have a positive oxidation state if they're combined with a more electronegative element. So these are some oxidation states, some common oxidation states of nonmetals and some ionic and covalent compounds. So again, the positive oxidation states is only if they're bonded to a more electronegative atom. So the first member of a nonmetal group tends to have different behavior than the other members, and this is because it has a smaller size, a higher ionization energy, and only has 4 valence orbitals. It has the 1 2s orbital and a 3 2p and 3 2p orbitals for bonding. So it doesn't have d orbitals, whereas the other members, as you go down the group, have an empty d orbital in their valence shell, so they can form more bonds because they have that extra orbital. The first members also have a greater ability to form pi bonds because they're smaller, so there's better atomic overlap with other atoms, with other smaller atoms. They can undergo redox reactions with nonmetals in general, and when this happens, they change oxidation states. Nonmetals tend to oxidize most metals. So for instance, if we take some iron and react it with some oxygen, we get iron oxide, iron 3 oxide. And so iron goes from having an oxidation state of 0, same with oxygen, and then iron ends with an oxidation state of +3, and the oxygen's of -2. So aside from nitrogen and carbon, which are poor oxidizing agents, more electronegative nonmetals are going to oxidize the less electronegative nonmetals, aka an anion. So for instance, if we have, let's look at this one, some chlorine, it's Cl2, so that means it has an oxidation state of 0, and it's reacting with I-, so it's a -1 oxidation state. It is going to give us I2, which now has a 0 oxidation state, and 2 Cl-. Fluorine and oxygen are the strongest oxidizing agents in their groups, and these oxidize all elements that are below them on the periodic table. Group 17 has the strongest oxidizing agents within their period. So as you're going across, period 2, for instance, your group 17 atom is going to be the strongest oxidizing agent in that period. And the stronger that a nonmetal is as an oxidizing agent, the more difficult it becomes to oxidize its anion. And then fluorine and oxygen are the strongest oxidizing elements known. Fluorine never ever forms compounds where it has a positive oxidation state. And oxygen generally doesn't, unless, and the only time it does is if it's bonded to fluorine. So if you have oxygen bonded to fluorine, then it's going to have a positive oxidation state because fluorine always has a negative one or 0. So for instance, if we take some 2F2, let me make that look a little prettier. So here fluorine has an oxidation state of 0, and we react it with some OH minus. Okay, then we get OF2, and here the oxygen has an oxidation state of +2 and 2F minus. So now fluorine is -1 and water. So ignoring noble gases, all of our nonmetals are going to form compounds with oxygen to form covalent oxides. So they're most of them are acidic and will react with water to form oxyacids, such as carbon monoxide, nitrous acid, and nitric oxide, though, are exceptions to this rule. We can also form acid anhydrides, and some examples are sulfur dioxide and dinitrogen pentoxide. And an acid anhydride, you have a nonmetal that is exhibiting one of its common oxidation states, and then when it reacts with water, there's no change in that oxidation state, and it produces an oxyacid as its product. So one example, if we take N2O5 and react it with water, we get 2HNO3. And if we look at this in N2O5, that nitrogen is, each nitrogen is going to have an oxidation state of +5, since you have 5 minus 2's from the oxygen, so that's -10, and then so we need 2 plus 5's to cancel that. And then in HNO3, we have 3 minus 2's from the oxygen, gives us -6. And then, let's see, where was I? And then 1 hydrogen is -1, or I'm sorry, is +1. So hydrogen is +1, so that brings us to a -5. So that means that the nitrogen has to have +5 to cancel it out. So you can see it still has the same oxidation state. This is an acid anhydride. Okay, now if you have an oxide where the nonmetal is not showing a common oxidation state, but it will still react with water, and then that nonmetal becomes both oxidized and reduced, you have a disproportionation reaction. Disproportionation reaction. That's a really hard word to say. So, for instance, we take some NO2, and here the nitrogen is +4, and we react it with water. We get 2 HNO3's. So here we have a +5 for the nitrogen. And NO. And in NO, nitrogen is +2. So you can see it was both reduced in that we reduced the oxidation state in NO and oxidized by increasing the oxidation state in HNO3. And then another thing to know is that the acid strength increases as the electronegativity of the central atom increases. So the next thing to know is that when we have binary hydrogen compounds like HCl, HBr, HI, HF, these show acidic behavior in water. But only HCl, HBr, and HI are strong acids. HF is a weak acid. And the acid strength of a nonmetal hydrogen compound is going to increase from left to right, going across a period and going down a group. So when it comes to structures of nonmetals, super different from non-metal structures super, super different from the metals. They have covalent bonds, some of them exist as individual molecules, and then you have electrons that are localized in covalent bonds. Whereas in ionic compounds, the electrons are kind of spread, they're delocalized throughout the whole solid, so they're all over the solid. Noble gases are monatomic, so you just have, helium gas by itself, but most of our other non-metal gases are diatomic, meaning, H2, N2, O2 in their natural state. Halogens, all of them are diatomic, and this includes liquid bromine and solid iodine. Even though bromine is liquid at room temperature, it's still Br2, and iodine is a solid, but it's still I2. And by seeing how these state changes in the halogens occur, so we're going from gas for F2 and Cl2, and then liquid for Br2, then solid for I2, we're seeing these atoms get bigger, so there's more interaction of London dispersion forces between the different molecules, which is why we're seeing these state changes. Oxygen has two allotropes, dioxygen O2 and ozone O3. Phosphorus has three allotropes that are common. There's other ones, but these are the common ones, red, white, and black. Sulfur has a bunch of different allotropes. And carbon has a bunch of allotropes like diamond, graphite, charcoal, carbon nanotubes, and graphene. So we're going to start with carbon. It has a bunch of different elemental forms. The first being diamond, and this is a hard, crystalline, colorless, and transparent compound when it's pure. So, when you're looking at diamonds, we always say you look for the 4 C's: cut, clarity, color. Oh God, I'm forgetting what the 4th C is. Nonetheless, so if it's not perfectly colorless, then you've got some impurities in it. Which, totally normal. Each atom has 4 single bonds to other 4 carbon atoms at the corners of a tetrahedron. So it's an sp3 hybridized, and has a very, very high melting point at 4,400 degrees Celsius. The next allotrope we have is graphite, and this is solid, soft, kind of slippery, grayish black, and it conducts electricity. Its structure has layers of carbon atoms, and each carbon is surrounded by 3 others in a trigonal planar arrangement. Each carbon forms 3 sigma bonds using sp2 hybrid orbitals. And then it has the unhybridized p orbital on each carbon, overlapping with the neighboring carbon's p orbital, giving us pi bonds. There's a bunch of resonance forms that have to occur to really describe the electronic structure of graphite. We're not really going to get into it, but just so you're aware. And you have these single layers, and you have London dispersion forces that are holding the layers together to give it this soft, flaky character, which is why we use it for pencils, because you're able to get these layers to just kind of slough off. And this is, like I said, pencil lead. There are other forms of carbon, like carbon black, charcoal, and coke. Carbon black is amorphous, and we get it from the incomplete combustion of methane, aka natural gas, CH4. Charcoal and coke we can make by heating wool and coal. Wood, not wool. Sorry, we're not shearing sheep here. Wood and coal at high temperatures in the absence of air. Interestingly enough, we've had some recent discoveries of some other allotropes. For instance, icosahedral carbon-60, which is called Buckminster fullerene, also known as buckyballs. We also have graphene, which is basically single sheets of graphite, and carbon nanotubes. So these are those first allotropes, A showing us a beautiful cut diamond, B graphite, and C is looking at the crystal structure of a diamond. You can see the 3-dimensional tetrahedrons. And then in D, you have the crystal structure of graphite. So you can see these different layers that we can then separate. And each layer, these are all 6-membered rings that are connected together. So this is also looking more at graphite. You have the unhybridized p orbitals. If you remember, those don't hybridize. So now they're able to overlap to make pi bonds. And then B, you can see a couple of the resonance forms of graphite with the double bonds kind of being shared. So one way that people might draw it, Please excuse my terrible drawing of hexagons. You'd think I'd be better from doing organic chemistry, but yeah, eventually you just get more lazy. Is you might see it kind of like this. Each corner represents a carbon, and then you see those circles in the middle, and those are the double bonds being shared over all the carbons. This is what Buckminster fullerene looks like. It's like basically a soccer ball. So you can see the different, you've got pentagons and hexagons to make this C60 shape, an icosahedral. Graphene is basically single sheets of graphite. And interestingly enough, one way that it's separated out is by using tape on graphite and peeling off a layer. And carbon nanotubes essentially is graphene that is put into a tube. So now let's talk about phosphorus. Its name comes from the Greek words meaning light bringing. This is because it glows in the dark, and it can burn when exposed to air, depending on which allotrope you're looking at. It is the only member of its group that actually occurs elementally in nature. So you can find phosphorus just as phosphorus in nature. Bunch of different allotropes, but we're just going to talk about the white and red allotropes. The white phosphorus allotrope is white, duh. It's waxy and melts at 44.2 degrees Celsius and boils at 280 degrees Celsius. It's insoluble in water, and so because of that, it tends to be stored in water, so it doesn't react with air. It's very soluble though in carbon disulfide and will burst into flames when exposed to air, hence why we need to store it in water. It exists in the form of P4 as a solid, liquid, gas, or even in solution, and it is very, very reactive and toxic. So white phosphorus is the bad phosphorus. And then we have red phosphorus that we get by heating white phosphorus to around 270 to 300 degrees Celsius without air. And this is denser than the white, has a higher melting point around 600 degrees Celsius. It's much less reactive, is non-toxic, and much easier and safer to handle. Its structure is polymeric, and so it's a bunch of 3D P4 networks that are joined by single phosphorus-phosphorus single bonds. It is insoluble, though, in solvents that dissolve white phosphorus. And when you heat it, though, you end up subliming off P4 molecules. So you still have to be careful. This is showing you white phosphorus stored in water in A, and then in B is showing you what its 3D structure looks like, the P4 molecules, and then in C is red phosphorus, much less reactive, and D is showing you the structure, and you can see how the tetrahedrons are linked by those phosphorus single bonds, and you can also see it just keeps going. All right, sulfur. Sulfur has very complex allotropy. That's a fun word. This is the brimstone that is referred to in things like the Bible and other places. Or, for my Shrek fans, when Donkey and Shrek are going to rescue the princess and they're coming up to the castle and they smell brimstone, right? It is the component recently discovered to be the component of Venus and Io's atmospheres. Io is a moon of Jupiter. The most stable and common allotrope of it is the yellow rhombic type, and this is what all of the allotropes of sulfur revert to when at room temperature. So if you take the crystals, they melt at 113 degrees Celsius, and then after cooling gives us a different allotrope, the long monoclinic sulfur needles that are stable from around 96 degrees Celsius up till their melting point of 119. Both rhombic and monoclinic sulfur have S8 molecules in 8-membered puckered rings, and each sulfur atom is bonded to each of its two neighbors by covalent sulfur-sulfur bonds. When you melt the rhombic form, it has this very low viscosity and high mobility, so we can pour it pretty easily. But then what happens if you continue to heat it, the sulfur bonds break at higher temperatures and you end up forming these polymeric chains that start tangling up with each other, making the liquid start to darken and become more and more viscous until around 230 degrees Celsius, where the liquid is too thick to even be able to pour. If you take this and rapidly cool it, you make what is called plastic sulfur, which is an amorphous solid and kind of rubber-like. At 445 degrees Celsius, the sulfur will start boiling and will form vapor of S2, S6, and S8 molecules. And this density of the vapor corresponds to actually S2 at 1000 degrees Celsius, and it's paramagnetic, much like O2. So these are the 4 allotropes here. 4 of sulfur's allotropes. Each have 8-membered puckered rings. You can kind of see the puckering in some of these rings here. So in A, you've got the S8 rings, B, S8 chains that are forming when those rings open. C, now we're adding sulfur atoms to the S8 chains, making longer chains, these polymers, and then D, when they start forming very long chains and tangling together. So the one thing that hopefully that you've noticed is overall all of our nonmetal structures tend to occur so they have 8 electrons in their valence shells. And they will do what they can to form enough covalent bonds to supplement the electrons that are already present in them to form an octet.